All right, good morning. It's time for us to go ahead and get started. It seems like our ranks have thinned a little bit this morning. How many people are taking an organic exam today? Nobody? Oh, that's where everybody is then. I got fresh candy, so we'll pass that around. All right, so some things I wanted to say about the exam. So this is pretty important. We're going to cover chapter 5, starting where we ended for chapter 2, for exam 2. So it's going to be sections 9 through 12. Math chapter E, chapter 6, and chapter 7 in its entirety. So there is a tiny bit of chapter 7 that we'll be covering on Monday. The other thing that's included on this is the concept of natural variables. That doesn't show up explicitly until chapter 8, but we've introduced it earlier. All right. The other thing is that I originally had said homework 10, all of it was going to be relevant to the exam. It turns out that it's only going to be the first 10 questions that are relevant to the exam. All right, so there's a review session today at 4:10, and then there'll be one on Sunday at 4:10, both in 11:04. We're going to try to do lecture capture on those so that those of you that can't make it, we will post it, assuming that it works. All right, things that we've talked about previously. We finished our discussion of heat engines. We derived an expression for the efficiency of a heat engine. Basically, we've seen that efficiency is given by the temperature differential between the hot reservoir and the cold reservoir over the temperature of the hot reservoir. We've also shown that we can calculate the entropy from a partition function, right? So this entropy that we get from partition functions, we call S spectroscopy, or spectroscopic. And that's because the partition functions that we've introduced depend upon the energy levels. And we've said that the energy levels for vibration, electronic, and rotational levels are determined from spectroscopy. So that's why that's called a spectroscopic entropy. We also showed that the entropy from the classical point of view is exactly the same as the entropy from the statistical thermodynamics point of view. And then from there, we talked about different ways to phrase the second law of thermodynamics. From there, we've introduced the third law of thermodynamics, and that's basically that entropy has an absolute value. And we've already alluded to the point that means that we have an absolute zero, and we've already stated that that absolute zero is going to occur at 0 Kelvin as long as my crystal is perfect. All right? And then last time we met, we showed that as we increase the temperature, we see an increase in the entropy. All right, so I wanted to take a moment to just review the natural variables. The last time we met, we derived this expression for ds. All right? And what we can conclude from this expression is that that's going to be the change in entropy due to a temperature change, and this is the change in the entropy due to a volume change, right? So by looking at that equation, we can conclude that entropy depends on temperature and volume, right? Now, if I look at the terms, this would be ds dt if I did a total differential. ds dt is the same as cv over t, all right? That's what we've shown last time. And then the rest of this is ds dv. Right? Now, if I look at those two equations and I see these derivatives, I see that they're not simple functions. It's not just a single variable, right? Here I have to take a derivative and I have to add something to it and divide it. Because those are not simple functions, then what we can say is that T and V, that is the variables that entropy depends upon, are not natural variables, right? And then just a comparison, we will show today that dH is the same as TdS plus VdP. So I look at that differential equation, and I step back and say that tells me that the enthalpy depends on entropy changes and changes in pressure. So we can say from this equation that enthalpy depends on S and P. All right? That means this first term is dH ds, and this second term is dH dP. All right? And we see that those are simple functions. Because these are simple functions, then we can conclude that entropy, S, and P, pressure, are natural variables for entropy. Okay? So that's what you're responsible for the exam at this point. Okay? All right, so some questions that we're going to ask today. How do we determine delta S for a phase transition? Some of the homework that was due today has not covered this explicitly, but given rise to our derivation. Then we're going to talk about absolute values of entropy. We're going to introduce standard molar entropy. Pretty much, if you think about that, what did we say that superscripted degree thing means? Anybody remember? It's standard state, but this is specifically 1 bar. Pressure 1 bar, all right? And then this means per mole. So standard molar entropy means the entropy per mole at 1 bar, right? From there, we're going to talk about qualitative determination of entropies for molecules. Again, some of the homework gave some clues as to this. And then from there, this is pretty much straight up what you did in Chem 178. You basically used Hess's law to calculate delta S for reactions, right? And I don't think we're going to quite get to the different temperatures for delta S of reaction today, but we'll get there on Monday. Okay? All right. So just a reminder, spectroscopic entropy, the book uses this symbol for it, S-calc, and that basically means entropy from partition function. Okay? All right, so moving forward, we are going to pick up where we left off last time. All right, so we have derived this expression for ds. Right? And then just a reminder, we're going to do a very similar derivation, but for starting with enthalpy rather than energy of the system. So instead of U, it's going to be H. And we're going to do a very similar parallel derivation. So at this point, I step back and say, all right, this total differential, ds, tells me that this is the change in the entropy due to a change in temperature. This is the change in entropy due to a change in volume. So what I can conclude is that Cv over T is the same as ds dt. And I can say that ds dv is this second term, and that will be 1 over T times du dv at constant T plus the pressure. Okay? We're going to be focusing on this equation, 7.2. I can do a rearrangement of that, and we can say that ds is equal to Cv T over T dt. All right? And if we look at that, that basically says, as long as I'm holding the volume constant, right, because that's this portion of the equation, if I hold volume constant, I can get delta S. Right? So we can integrate this. This will get me delta S is equal to the integral from T1 to T2 Cv over T dt. Okay? All right, so as long as we're talking about a constant volume process, I can calculate the entropy at any temperature for my substance using the heat capacity and the temperature. Right? What we've derived so far is true as long as we don't have a phase change in this temperature range that we're integrating. Right? And we're going to see how to deal with phase transitions in a little bit. Okay? So the other thing that we can say is that we know that Cv is always a positive value, and then T, because it's absolute, is also positive, right? And so if I have, so these guys are both positive, so if my temperature goes up, that also tells me my entropy goes up. And we've previously seen that, right? So this says as T increases, S increases also, okay? All right, and then practically, how can we use this? Well, this says I can go into the laboratory, measure heat capacity data. I can measure heat capacities as a function of temperature, and that allows me to determine what the entropy change is, right? So I'm going to draw a little tiny graph here. Cp over T as a function of T, the area under that curve is going to correspond to delta S. Okay? It's the area under a curve of Cp over T as a function of temperature. All right? Now we're going to come back to this. Whoops, that's supposed to be Cv. Oops, and I just wrote P again. Damn me. Cv. Okay. All right. That'll make sense? All right, so we're not going to be spending too much time talking about this because most processes that we're interested in aren't conducted at constant volume, right? In the real world, when we have things open to the atmosphere, it's constant pressure that's important. So we're going to be talking about the constant pressure side. And that's our next derivation that we're going to do. All right? So this is the derivation that I said parallels what we've done for U and S. Okay? All right, so where we're going to start is we're going to start with the definition of enthalpy, and that's given by U plus PV. Right? And just as we did when we talked about U, we did the differential of that. So this is going to be the differential of U, du, plus the differential of P times V. And that's going to be P dV plus V dP, right? Because I have a product, P times V. That makes sense? All right? So the other thing that we can do is we can say, well, we have just shown that du is the same as TdS minus PdV. So I can plug that into that, all right? And I've got minus PdV here, and I've got plus PdV here, so they go away, right? And so at this point, what I can say is that dH is the same as TdS plus VdP. Okay? Make good? Make sense? All right, and then, we started our discussion today talking about this explicitly. dH is a function of changes in entropy, changes in pressure. So H is a function of S and P. This is ds, or dH ds. This is dH dP. And is that a simple function? Looks simple to me, right? And that's a simple function. So what we can say is that those two quantities, and let me just write that down, S and P are natural variables of enthalpy. Okay? All right, so we also can say H is a function of T and P, right? So again, thinking about the derivation we did last time, we started by saying U is a function of T and V. So we're going to say H depends on T and P now, and then I can do a total differential, right? So that says dH is going to be given by dH dt, holding pressure constant, times dt, plus dH dP, holding temperature constant, times dP, right? And just like we did in the previous derivation, we set these two equal to each other. dH is equal to dH, so TdS plus VdP becomes equal to this differential, and then we can take that equation and solve for ds. Okay? And that's exactly what we did for internal energy previously. All right, bear with me for a second. Okay, so at this point, we can say that dsD is equal to, right? And before I go there, let's just remind her of something. We've got a dH dt in here, right? And that's the definition of constant pressure heat capacity, all right? So ds will be equal to Cp, function of T over T dt, plus 1 over T times dH dP at constant temperature minus the volume times dP. Okay? All right, so now we look at this and we say this means that entropy depends on changes in temperature, depends on changes in pressure. So Cp over T is going to be ds dt, right? And then this other side, 1 over T dH dP minus V, all is the same as ds dP. Okay? All right, now we step back and we look at this and we say, all right, so here I'm going to change the color of the pen a little bit. So I look at this equation. This says S is a function of T and P. All right? But when I look at the differentials, ds dP and ds dt, those aren't simple functions. Right? And so what we can say is that T and P are not natural variables. For entropy. Okay? All right, and this parallels what we've just covered. So I focus on this portion of the equation, and I can say that at constant pressure, ds is going to be given by Cp over T dt. And I can integrate that, right? And that basically says if I want to know the entropy at one temperature relative to another temperature, I need to integrate between the two temperatures and use the heat capacity. Okay? So it's exactly the same relationship as we saw for constant volume, but under constant pressure, we're going to use the heat capacity for constant pressure. Okay? All right. And then if we think about it, if we're doing an experiment and we start at 0 Kelvin, we're going to be integrating from 0 up to whatever temperature we're interested in. And what I need to do is just add to that what my entropy is at 0 Kelvin. Okay? Right? And if I have a perfect crystal, we expect it's going to be 0, right? Okay? All right, so just as we saw previously, this is true as long as there is no phase transition 0 to T2. All right, so this just shows how one uses calorimetric data, heat capacities, to get the entropy. All right, so when the limit of 0 approaches 0, I expect to be my minimum in the heat capacity over the temperature. I've got temperature on this axis. I'm going to choose this to be T prime. And if I wanted to know what entropy was at T prime relative to 0 Kelvin, I'm going to integrate this area, and that will give me this point down here. Okay? So that'll be S at T prime. Okay? Does that make sense to everybody? All right. Okay, so if I want to know what the entropy of a substance is at some temperature, I need to know the 0 point, right, S at 0, and I also need to know what the entropy change is at phase transition. So I almost forgot to talk about that here. Right? So one of the things we see is that our heat capacity over temperature curve is continuous until we get to a phase transition. Right? And this jump here is going to be due to the entropy change associated with that phase transition. In this case, it's melting. In this case, it's vaporization. We need to get a handle on how to calculate that. We're going to do that momentarily. Okay? All right. Section 7.2 basically is another expression of the third law. S at 0 K of perfect crystal is 0. Okay? Whoops. Keep getting the book. All right. So that's what this says here as well, so we don't need to say it again. The easiest way for us to see this is to look at it from the statistical thermodynamics point of view. We know that S is Kb ln W. If I'm at 0 Kelvin and I have perfect order, we know that W, there's only one way to arrange the system, right? This is when you think about dice or you think about pennies, right? You go to low temperatures, they're all heads or they're all 2. There's only one way to get there, so that means W is equal to 1, and therefore we end up with entropy equal to 0. All right, so section 7.3, we're going to talk about delta S for a phase transition, right? So TRS is going to be our symbol for phase transition. All right, and what we're going to show is that that's the same as delta H of the phase transition over the temperature of the phase transition. Okay? All right, so this is what we want to show. Okay? All right, so the thing we need to think about is if we're at a phase transition, right? We think about going into the lab, doing an experiment, right? I start with ice below 0 degrees. We're going to say we're at 1 atmosphere, right? I have ice at 0 degrees, and I add a little heat to it. What's going to happen to the ice? It's going to melt, right? Right? Does the temperature change in converting from ice to liquid? It doesn't initially, right? If you add heat to the system, you see as long as it's solid, you're just heating the solid. And then as soon as you hit 0 degrees, you see a constant temperature until you get into the liquid phase, right? And that's really important because that says if I'm at 0 degrees, I have equilibrium between the solid and the liquid, right? And if you think about it, if I make an infinitesimal increase in temperature, I go liquid. Infinitesimal decrease in temperature, I go solid. That's the definition of a reversible process, right? Infinitesimal change, one direction, I get reversed exactly by going the opposite direction. All right. So we can say phase transitions are isothermal, right? Because we have both phases present at the same temperature, and they're reversible. All right, so I'm going to come back up here and say, well, delta S of our phase transition, we go back to the definition of entropy. That's going to be the integral of dq reversible for the phase transition divided by the temperature of the phase transition. Because it's isothermal, I can pull the temperature out in front. All right? That's the only reason I can do that is because this isn't changing in the phase transition. And then I have the integral of dq reversible at the phase transition, right? And we know that the integral of dq is simply going to be the heat transfer, right? So that's equal to q reversible of the phase transition over the temperature of the phase transition, okay? All right, when what I've determined here is absolutely general. To get from here to delta H, that's the heat transfer at constant pressure. Okay? So at constant P, this becomes delta H of the phase transition over the temperature of the phase transition. Okay? Does that make sense? All right, and then I'm not going to write this down, but just to cover bases and give another example, we know that the delta S is going to be the heat transfer over the temperature, at the phase transition. If I choose a constant volume path, then it isn't delta H. Does anybody remember what it is? It's going to be delta U. All right? So if we were talking about a constant volume process, it would be delta U over T. Okay? All right, so at this point, we can calculate the entropy from calorimetric data. All right, so we start at 0 degrees Kelvin. We go up to a melting point. We use the heat capacity that's associated with the solid phase over the temperature. That integral gets me up until I get to the melting point. And then to get through the melting point, I use delta S of the phase transition, which is going to be the enthalpy change over the temperature. And then I go from the melting point up to the vaporization point. This will be heat capacity of the liquid phase. And then this gets me through the phase transition going from liquid into gas phase. Right? So we have a way to calculate entropy. Right? Okay, section 7.4. This is just making a statement. As T approaches 0, heat capacity also approaches 0. Unfortunately, we don't have enough time to go into this in any depth. All right? But we can say if we look at experiments and we look at theory, they both predict the same thing. As heat capacity at low temperatures has a T cubed dependence. Right? And so as T goes to 0, that tells me my heat capacity for the solid phase is going to be approaching 0 as well. Okay? All right, so in the next section, we're basically just going to apply some of this. So in this case, calorimetry. And this is going to be heat capacity data, Cp, and delta H of phase transitions allow us to determine entropy. All right? And that's an absolute value. Okay? All right. So this basically shows the entropy per mole as a function of temperature, specifically for nitrogen at 1 bar. So I want to talk through how we would calculate that, right? So in this high temperature region, you expect nitrogen to be in what phase? It's going to be in the gas phase. So all along that curve, that's going to be the result of the integral from T vaporization to whatever T I'm interested in, Cp for the gas phase over T dt. Okay? So that allows us to calculate entropy up at these higher temperatures. This region is going to correspond to delta S of what? It's going to be vaporization, the phase transition, right? So this portion, delta S vaporization, and that's going to be given by delta H of vaporization over the temperature of vaporization, right? And then this little region corresponds to when nitrogen is a liquid. So entropy in that case will be from the integral T fusion, the melting point, up to T vaporization. I'm going to have my heat capacity, but now it's going to be the liquid phase, reference to temperature, times dt. All right? Just to avoid confusion here. Where I'm going straight up and down, this is going to correspond to delta S associated with melting or fusion, right? So that's going to be delta S fusion, which we know is equal to delta H of fusion over the temperature of fusion per mole. Okay? All right. And then we see this little area here. So we see this continuous function, discontinuity, and then continuous. Does anybody know what that's caused by? Is it a phase transition? Well, every time that we see that this goes straight up, it has to be a phase transition, right? So it's not sublimation, right? So think about, I mean, this is nitrogen, but carbon comes in different forms, right? In the solid, it can exist as graphite, it can exist as diamond, right? So this represents a solid-solid phase transition. And delta S of that phase transition will be given by delta H of the phase transition over the temperature. And then in this region and this region, we would use the heat capacity over temperature for those forms of the solid. Does that all make sense? Okay? All right, so at any rate, we now have a clear way using calorimetric data, right? I go into the lab, I measure the temperature as a function of heat, that gives me the heat capacity, and I can measure delta H's for the phase transitions, and that allows me to calculate what the absolute value of the entropy is, right? So this just summarizes everything that was shown in that previous graph. So this is just a table that's the source of that data, all right? Okay, section 6. And this is review from the last chapter. Absolute entropies can be calculated from partition functions. So the last time we met, we derived the expression where we saw the entropy that we calculate is given by the energy over the temperature, which is kBT, times the partial of the ln of Q with respect to T, holding N and V constant, plus KB ln Q, right? And in your homework, you had the opportunity to calculate an absolute value of entropy, okay? All right, so it turns out that this, as you saw in the homework that was due today, you get excellent agreement with experiment. And if you have a deviation from experimental data, this is more likely to be closer to the accurate value. And we'll see why that is in a little bit. Okay, so before we get there, I do want to talk about qualitative identification of relative entropies, right? And this should hopefully make a lot of sense. So this is going to be S naught per mole. All right, that's our standard molar entropy. All right, so it's the substance entropy per mole whenever I have a pressure of 1 bar. All right, and what we're going to see is that they depend upon the mass and structure. Okay? All right, so let's talk about the relationship between entropy and the mass. All right, keep in mind that entropy is a measure of disorder, apparent disorder, or randomness, right? And if you think about it, if I have 1 penny, I can have one or head or tail. If I have 2 pennies, I've got 4 different ways to arrange it, right? So 2 pennies inherently have a higher entropy than 1 penny. Does that make sense? All right? So it's the same concept that we've got going on here. So if I think about the mass portion of this, I go back to our energy levels for translation. So we see that mass is in the denominator. And what we've seen is that when we increase the mass, the energy level spacing is closer. Right? Greater molar mass, closer energy level spacing. And that basically means that our particles have more energy levels that are available to them at a given temperature. Right? So more translational states available. And if I have more translational states available to my particles, what's going to be true of the entropy? If I have 4 pennies versus 1, I have more states available. All right? So this leads to greater entropy. Okay? All right, so let me take a moment to look at this graph. So this shows standard molar entropies as a function of the natural log of the mass. So as the mass goes up, the natural log of the mass is going up. So here we're looking at noble gases, right? They're all 1 atoms, right? So these are monoatomic gases, particles. And it's pretty clear that as I increase the mass, I see an increase in the entropy, right? And that directly falls from what we've just stated, okay? All right, so the other thing that we need to think about is if we have more atoms in our molecule, right? So now we're not looking at mass, we're looking at the number of atoms. And what we've seen is that if I have 1 atom, I don't have any vibrational modes available. If I have 2 atoms, I have 1. If I have 3 atoms, I have 3n minus, 2 minus 6 or 5, right? Depending on the shape of the molecule, right? So the more atoms I have, the more vibrational levels that I have available. All right? And so this is basically more like comparing a penny with a die, right? A penny's got 2 possibilities. If I go to a die, I've got 6 possibilities. Who's got greater entropy? The die, right? Right? And that's pretty much what we see, in this graph. So if we go from noble gases, single atoms, same mass, we see an increase in the entropy, and this is due to the fact that I have some vibrational modes. Okay? Does that make sense? If I have 3 atoms, I'm going to have further increase. Right? So I don't want to take a lot of time to talk about this data, but just things that you expect to be true are going to be supported here. If I said, what phase has the lowest entropy associated with it, you're going to say the solid state. And sure enough, we look at solids, and those are the lowest ones that we've got, right? And then I compare like I2 with graphite. We see, yeah, it's still pretty high. That's because I2 is really massive, right? Right. So, and then we look as who's got the greatest entropy. That's going to be the gas phase, right? So I look at the column. I look for the largest values. 248, 238. These are all in the gas phase, right? So by looking at this data, what we can say is that S of the solid is less than S of the liquid, which is less than S of the gas phase. Okay? Right? And that's whether we're talking about 1 bar or 10 bar, as long as we're comparing at the same pressure. Okay? All right. So implications that this has, and this is also relevant to the homework that's due next Friday and the exam. So if I have a chemical reaction and I want to predict what delta S is, then I look to see what the phase transitions are. Right? So if I'm going from solid reactants, you write solid reactants to liquid products, what do you expect delta S to be for this reaction? You expect it to be positive, right? The entropy of the products are greater than that of the reactants. So delta S of the reaction is greater than 0, right? And if I go from liquid reactants to gas phase products, we expect the same thing. Okay? All right. So this allows us to predict qualitatively. And then we can say, well, if I have a gas phase reaction, all right, so if gas phase reaction and let me just write one down. Let's say we're going to go from N2 plus H2 to NH3. All right, so I have 2 moles of gas produced. I'm going to need 3 moles of hydrogen and 1 mole of nitrogen. All right. So in this case, everybody's in the gas phase. I end up with 2 moles of gas. I started out with 4 moles of gas. So what do you think delta S for this reaction is going to be? It's going to be negative, right? Qualitative, we can predict that. Right? So for gas phase reaction, delta N for the number of moles of gas determines sign. Okay? Make sense? All right, so we've talked about the relationship between phase, mass, and the number of atoms. So next up, we're going to talk about the structure. All right? So in this example, we're going to see that we have 2 isomers. So I've got acetone and I've got trimethylene oxide. They have the same atoms in them, therefore they have the same mass. Right? So if you think back to Gen Chem and organic, if I was to look at this portion of the molecule, we expect that methyl group to be able to rotate, right? Can this CH2 rotate? No, it's fixed, right? So I've lost rotational possibilities here, right? And then if the other way to think about this, if this was a long chain, I could move that chain all over the place. If I hoop the chain, I've limited the number of degrees of freedom that are available to that molecule. Does that make sense? All right, so which one of these is going to have the greater entropy? Acetone or trimethylene oxide? It's going to be acetone, all right? Now, it's not hugely different, but it definitely is different. So acetone is 298 joules per K per mole, and trimethylene oxide is 274 joules per K per mole, all right? So what we can say is that if we have molecules with the same molecular mass, the more compact the molecule, the lower the entropy, right? So this also, correlate with, let's say that I have, octane versus the compact form of octane. What does it be? Isooctane, right? Versus N-octane. Isooctane is going to have a lower entropy than N-octane. Range structure has a lower entropy. Okay? All right, so let's talk about determination of delta S for a reaction if I know it at one temperature but not at other temperatures. So we're going to look at our example, is going to be bromine. So at 1 bar, bromine goes from the boiling point of bromine is 332 Kelvin. Right? So I should be able to calculate that delta S, So delta S vaporization for bromine will be delta H vaporization over temperature of vaporization. And basically what I've told you is that's at 332 Kelvin. Okay? Well, let's say that I'm interested in knowing what the entropy change is if I did that same process at room temperature, right? But physically, it's not going to be easy for me to do that process, right? But I can ask, if I could do it, what's that delta S, right? And what I can do is what we've done previously, is I can say, well, I can start with my reactant at this temperature, change its temperature, let the reaction proceed, and then return to the temperature that I'm interested in, right? All right, so we can say then that we've got delta S for path 1, delta S for path 2, delta S for path 3, all right? And the sum of those will get me delta S for what I'm interested in knowing, okay? All right, so now we think about what we're doing here, we're talking about an entropy change, right? And so now we go back to what we've derived earlier today and last time we met. So delta S for path 1 is going to be equal to the integral, in this case from 298 to 332 of the heat capacity of the liquid over the temperature dt, right? And delta S for path 3 is going to be the integral from 332 to 298 of Cp over T, but now the heat capacity for the vapor phase. Okay? And then delta S2 is just going to be the entropy change at 1 bar. All right, so delta S overall at 298 will equal delta S1 plus delta S2 plus delta S3. All right? So because entropy is a state function, this allows us to calculate this path. Make sense? All right, so one of the things that we recognize is that what we needed to use was Cp over T in order to determine the entropies for the heating and cooling paths. Okay? All right, section 8. So I'm going to try to go through this a little bit slowly. How are we doing on time? We're doing great on time, actually. Okay, so in this case, S calculation, which again is our spectroscopic entropy, is sometimes greater than S experiment, where experiment means calorimetry. Okay? And just make sure that we get what I'm talking about. This is S from the partition function. This is S from heat capacities and delta H's, right? And what we find is that sometimes we see that the partition function generated entropy is greater than that of the calorimetry. The difference between the two is called the residual entropy. All right? And then we can ask the question, why is this? Right? And it turns out that if you think about an experiment where you're doing a calorimetry experiment, so I start with a substance at room temperature, I cool it down, cool it down, cool it down. How likely do you think it is that at 0 Kelvin I'm going to have a perfect crystal? It's not easy to do, right? Right? And one easy example to look at, and we'll cover this in a little bit more detail next time, is looking at carbon monoxide. So carbon monoxide has almost no dipole moment, right? So as I condense it and put it into the solid state, there's no energetic reason for a CO to be lined up with a CO, with a CO, with a CO. So that really means that energetically, if I do the freezing process, I don't expect to get a perfect crystal, right? Just like if you think about if I had a whole mess of pennies, for me to try to get them all heads, I've got to do some work to get there, right? That's not going to randomly occur, right? And so what we see is that at 0 Kelvin, I have two orientations available, right? And if you think back to it, that basically says S is not equal to 0 when the crystal is imperfect. And if I have a random arrangement of my substances, this entropy at 0K is going to be given by Kb times Ln. So S at 0 will be Kb ln Z, where Z is the number of random orientations that are available to the molecule. Okay? Molecule. All right, and for CO, it's going to be CO or OC, so there's only two, right? And that's where we'll pick up next time, which conveniently is a good time for us to stop. All right, have a good afternoon. Reminder, today at 4, there's a review session. Sunday, there's a review session.